atoms in a unit cell. So in all our discussions, we'll be talking about the cubic unit cell. So this is a cube. In this, all the three sides are equal, length, breadth and height. Now in order to count the number of atoms for a particular unit cell, we mean that what volume of a particular atom is included in a unit cell. Now, for example, this is a crystal lattice, right? This hole is a crystal lattice because it is formed from a number of unit cells. This one is the first unit cell, behind this is another one, and this is another one, and behind this also there is another unit cell, and below this and behind this one, and like this we have a total of 1, 2, 3, 4, 5, 6, 7 and 8. 8 unit cells combined together. So for example, an atom is kept at the center of this whole big lattice. When it is kept at the center, the number of unit cells of which it forms a part, which means that the number of unit cells in which this atom is included is equal to 8. 4 from below and 4 from the above. Now if I ask you that what volume of this atom is included in one unit cell, that would be 1 divided by 8, because we have one atom and that is present in 8 unit cells. So 1 by 8 volume is present for one unit cell. Therefore, we conclude that each atom at a corner is shared between 8 adjacent unit cells, and hence only 1/8 of an atom belongs to a particular unit cell. Now for a primitive unit cell in which the atoms occupy just the corner positions, the total number of atoms that would be present in one unit cell would be equal to 8, which is because 8 corners are there, so 8 atoms into 1 by 8, because each atom gives a volume of only 1 by 8 to this unit cell. So 8 multiplied by 1 by 8 gives us 1 atom. So here we can say that a volume of only 1 atom would be included for a primitive unit cell. Similarly, we calculate it for the body-centered cubic unit cell. Now, in a body-centered cubic unit cell, in addition to the atoms present at the corners, we also have one atom present at the center of this cube. Now, since it is present at the center of the cube, the whole volume of this atom would be included in the cube, and so we calculate the total number of atoms as 8, which are present at the corner, multiplied by 1 by 8 per corner atom, which gives us 1 atom, and the second one would be 1 atom that is present at the body center, and so the total number of atoms become 1 plus 1, which is equal to 2 atoms. In the similar manner, we calculated for face-centered cubic unit cell. Here we have atoms at the corners of the unit cell and also at 6 faces of the unit cell. Now because the atom is present at the face of this unit cell, half of it is present inside the unit cell and half of it is present outside the unit cell. So the volume actually included inside would be of only half atom. Therefore, the total number of atoms would be calculated by first calculating for the corner atoms, which are equal to 8 into 1 by 8, which is equal to 1 atom. The second one would be for 6 face centers. So 6 multiplied by half, because each atom contributes just half the volume, which gives us 3 atoms, and therefore the total number of atoms become 1 plus 3 equals 4 atoms. Next we calculate the packing efficiency or the packing fraction for a particular unit cell. So as we saw various unit cells and the atoms present in them, we noticed one thing, that no matter how many atoms are present in the unit cell, but some of the space is, we calculate the percentage of total